A tantalum electrolytic capacitor, a member of the family of electrolytic capacitors, is a polarized capacitor whose anode electrode is made of tantalum on which a very thin insulating oxide layer is formed, which acts as the dielectric of the capacitor. A solid or liquid electrolyte which covers the surface of the oxide layer serves as the second cathode electrode of the capacitor. Because of its very thin and relatively high permittivity dielectric layer, the tantalum capacitor distinguishes itself from other conventional and electrolytic capacitors in having high capacitance per volume and lower weight. Most tantalum capacitors are available as surface-mount devices with a solid manganese dioxide, a solid polymer electrolyte. A solid electrolyte ensures low equivalent series resistance and a stable electrical behavior over a broad temperature range. The high specific capacitance of tantalum capacitors makes them particularly suitable for passing or bypassing low-frequency signals up to some megahertz and storing larger amounts of energy to support the power rails of highly integrated circuits. Especially the SMD version with its small size and weight make tantalum capacitors attractive for flat or small products. However, due to the cost of tantalum ore, tantalum electrolytic capacitors are considerably more expensive than comparable aluminum electrolytic capacitors. Tantalum capacitors are polarized components. Reverse voltage or ripple currents higher than specified can destroy the dielectric and thus the capacitor. For safe operation of tantalum capacitors, special circuit design rules are specified from the manufacturers. Materials, production and styles. Anode tantalum capacitors are manufactured from a powder of relatively pure elemental tantalum metal. A common figure of merit for comparing volumetric efficiency of powders is expressed in capacitance times volts per gram. Since the mid-1980s, manufactured tantalum powders have exhibited around a 10-fold improvement in CV per gram values. The typical particle size is between 2 and 10 micrometers. Figure 1 shows powders of successively fine grain, resulting in greater surface area per unit volume. Note the very great difference in particle size between the powders. The powder is compressed around a tantalum wire to form a pellet. The riser wire ultimately becomes the anode connection to the capacitor. This pellet wire combination is subsequently vacuum sintered at high temperature, which produces a mechanically strong pellet and drives off many impurities within the powder. During sintering, the powder takes on a sponge-like structure, with all the particles interconnected into a monolithic spatial lattice. This structure is of predictable mechanical strength and density, but is also highly porous, producing a large internal surface area. Larger surface areas produce higher capacitance. Thus high CV per gram powders, which have lower average particle sizes, are used for low voltage, high capacitance parts. By choosing the correct powder type and sintering temperature, where specific capacitance or voltage rating can be achieved. For example, a 220 microfarad 6 volts capacitor will have a surface area close to 346 square centimeters, or 80% of the size of a sheet of paper. Although the total volume of the pellet is only about 0.0016 cc. The dielectric is then formed over all the tantalum particle surfaces by the electrochemical process of anodization. To achieve this, the pellet is submerged into a very weak solution of acid and DC voltage is applied. The total dielectric thickness is determined by the final voltage applied during the forming process. Initially, the power supply is kept in a constant current mode until the correct voltage has been reached. It then holds this voltage and the Current decays to close to zero to provide a uniform thickness throughout the device and production lot. The chemical equations describing the dielectric formation process at the anode are as follows: 2Ta 5 10 E minus 2Ta 5 10 O minus Ta2O5 5 H2O. The oxide forms on the surface of the tantalum, but it also grows into the material. For each unit thickness of oxide growth, 1/3 grows out and 2/3 grows in. Due to the limits of oxide growth, there is a limit on the maximum voltage rating of tantalum oxide for each of the presently available tantalum powders. The dielectric layer thickness generated by the forming voltage is directly proportional to the voltage proof of electrolytic capacitors. Electrolytic capacitors are manufactured with a safety margin in oxide layer thickness, which is the ratio between voltage used for electrolytical creation of dielectric and rated voltage of the capacitor. To ensure reliable functionality, the safety margin for solid tantalum capacitors with manganese dioxide electrolyte is typically between 2 and 4. That means that for a 25 volts tantalum capacitor with a safety margin of 4, the dielectric voltage proof can withstand 100 volts to provide a more robust dielectric. This very high safety factor is substantiated by the failure mechanism of solid tantalum capacitors, field crystallization. For tantalum capacitors with solid polymer electrolyte, the safety margin is much lower, typically around 2. Cathode. The next stage for solid tantalum capacitors is the application of the cathode plate. This is achieved by pyrolysis of manganese nitrate into manganese dioxide. The pellet is dipped into an aqueous solution of nitrate and then baked in an oven at approximately 250 degrees Celsius to produce the dioxide coat. The chemical equation is Mn2 manganese 2 peroxide plus 2NO2. This process is repeated several times through varying specific gravities of nitrate solution to build up a thick coat over all internal and external surfaces of the pellet, as shown in Figure 4. In traditional construction, the pellet is successively dipped into graphite and then silver to provide a good connection from the manganese dioxide cathode plate to the external cathode termination. Production flow. The picture below shows the production flow of tantalum electrolytic chip capacitors with sintered anode and solid manganese dioxide electrolyte. Styles of tantalum capacitors. Tantalum electrolytic capacitors are made in 3 different styles. Tantalum chip capacitors, SMD style for surface mounting. 80% of all tantalum capacitors are SMDs. Tantalum pearls, resin-dipped, single-ended style for PCB mounting. Axial-leaded tantalum capacitors, with solid and non-solid electrolyte, mostly used for military, medical and space applications. Different styles of tantalum capacitors. Chip capacitors. More than 90% of all tantalum electrolytic capacitors are manufactured in SMD style as tantalum chip capacitors. It has contact surfaces on the end faces of the case and is manufactured in different sizes, typically following the EIA 535B AAC standard. The different sizes can also be identified by case code letters. For some case sizes, which have been manufactured for many decades, the dimensions and case coding over all manufacturers are still largely the same. However, new developments in tantalum electrolytic capacitors such as the multi-anode technique to reduce the ESR, the face-down technique to reduce the inductance have led to a much wider range of chip sizes and the case codes. These departures from EIA standards mean devices from different manufacturers are no longer always uniform. An overview of the dimensions of conventional tantalum rectangular chip capacitors and their coding is shown in the following table. Note: EIA 3528 metric is also known as EIA 1411 imperial. Wet tantalum capacitors. The main feature of modern non-solid tantalum electrolytic capacitors is their energy density compared with that of solid tantalum and wet aluminum electrolytic capacitors within the same temperature range. Due to the self-healing properties, the dielectric thickness can be formed with much lower safety margins and consequently with much thinner dielectric than for solid types, resulting in a higher CV value per volume unit. Additionally, wet tantalum capacitors are able to operate at voltages in excess of 100 volts up to 630 volts, have a relatively low ESR, and have the lowest leakage current of all electrolytic capacitors. The original wet tantalum capacitors developed in the 1930s were axial capacitors, having a wound cell consisting of a tantalum anode and foil cathode separated by a paper stripe soaked with an electrolyte, mounted in a silver case and non-hermetic elastomer seal. Because of the inertness and stability of the tantalum dielectric oxide layer against strong acids, the wet tantalum capacitors could use sulfuric acid as an electrolyte, thus providing them with a relatively low ESR. Because the silver case in the past had problems with silver migration and whiskers, which led to increasing leakage currents and short circuits, new styles of wet tantalum capacitors use a sintered tantalum pellet cell and a gelled sulfuric acid electrolyte mounted in a pure tantalum case. Due to the relatively high price, wet tantalum electrolytic capacitors have no consumer applications. They are used in rough industrial applications, such as in probes for oil exploration. Types with military approvals can provide the extended capacitance and voltage ratings, along with the high-quality levels required for avionics, military and space applications. History. The group of valve metals capable of forming an insulating oxide film was discovered in 1875. In 1896, Carroll Pollock patented a capacitor using aluminum electrodes and a liquid electrolyte. Aluminum electrolytic capacitors were commercially manufactured in the 1930s. The first tantalum electrolytic capacitors with wound tantalum foils and non-solid electrolyte were developed in 1930 by Tantalum Electronic Inc., USA, and were used for military purposes. Solid electrolyte tantalum capacitors were invented by Bell Laboratories in the early 1950s as a miniaturized and more reliable low-voltage support capacitor to complement the newly invented transistor. The solution R.L. Taylor and H. E. Herring from the Bell Labs found for the new miniaturized capacitor found in early 1950 was based on experience with ceramics. They ground down tantalum to a powder, pressed this powder into a cylindrical form and then sintered the powder particles at high temperature between 1500 and 2000 degrees Celsius under vacuum conditions to a pellet. These first sintered tantalum capacitors used liquid electrolyte. In 1952, Bell Labs researchers discovered the use manganese dioxide as a solid electrolyte for a sintered tantalum capacitor. Although the fundamental inventions came from the Bell Labs, the innovations for manufacturing commercially viable tantalum electrolytic capacitors were done by the researchers of the Sprague Electric Company. Preston Robinson, Sprague's director of research, is considered to be the actual inventor of tantalum capacitors in 1954. His invention was supported by R. J. Millard, who introduced the reform step in 1955. A significant improvement in which the dielectric of the capacitor was repaired after each dip and convert cycle of manganese to peroxide deposition. This dramatically reduced the leakage current of the finished capacitors. This first solid electrolyte, manganese dioxide, had 10 times better conductivity than all other types of non-solid electrolyte capacitors. In the style of tantalum pearls, they found very quick broad use in radio and new television devices. In 1971, Intel launched its first microcomputer. In 1972, Hewlett-Packard launched one of the first pocket calculators. The requirements for capacitors increased, especially the demand for lower losses. The equivalent series resistance for bypass and decoupling capacitors of standard electrolytic capacitors needed to be decreased. Although solid tantalum capacitors offered lower ESR and leakage current values than the aluminum electrolytics, 1980 a price shock for tantalum in the industry dramatically reduced the usability of tantalum capacitors, especially in the entertainment industry. In search of cheaper alternatives, the industry switched back to using aluminum electrolytic capacitors. The development of conducting polymers by Alan J. Heeger, Alan McDiarmid and Hideki Shirakawa in 1975 was a breakthrough in point of lower ESR. The conductivity of conductive polymers such as polypyrrole or PEDOT are better by a factor of 1,000 than that of manganese dioxide, and are close to the conductivity of metals. In 1993, NEC introduced their SMD polymer tantalum electrolytic capacitors, called NeoCap. In 1997, Sanyo followed with their POSCAP polymer tantalum chips. A new conductive polymer for tantalum polymer capacitors was presented by Chemet at the 1999 CARTS conference. This capacitor used the newly developed organic conductive polymer PEDT poly, also known as PEDOT. This development to low ESR capacitors with high CV volumes in chip style for the rapid-growing SMD technology in the 1990s increased the demand on tantalum chips dramatically. However, another price explosion for tantalum in 2000-2001 forced the development of niobium electrolytic capacitors with manganese dioxide electrolyte, which have been available since 2002. The materials and processes used to produce niobium dielectric capacitors are essentially the same as for existing tantalum dielectric capacitors. The characteristics of niobium electrolytic capacitors and tantalum electrolytic capacitors are roughly comparable. Reliability and lifetime. Reliability. The reliability of a component is a property that indicates how well a component performs its function in a time interval. It is subject to a stochastic process and can be described qualitatively and quantitatively. It is not directly measurable. The reliability of electrolytic capacitors are empirically determined by identifying the failure rate in production accompanying endurance tests. See reliability engineering #reliability testing. The reliability normally is shown in a bathtub curve and is divided into 3 areas: early failures or infant mortality failures, constant random failures, and weird failures. Failure types included in the total failure rate are short circuit, open circuit, and degradation failures. The reliability prediction is generally expressed in a failure rate lambda, abbreviation fit component hours of operation at fixed working conditions during the period of constant random failures. These failure rate model implicitly assume the idea of random failure. Individual components fail at random times but at a predictable rate. The standard operation conditions for the failure rate fit are 40 degrees Celsius and 0.5 Er. The reciprocal value of fit is mTbF. For tantalum capacitors, often the failure rate is specified at 85 degrees Celsius and rated voltage U as reference conditions and expressed as % failed components per 1000 hours. That is n number of failed components per 105 hours, or in fit the 10,000-fold value per 109 hours. For conditions other than the standard operation conditions 40 degrees Celsius and 0.5 for other temperature and voltage applied, the current load, capacitance value, circuit resistance, mechanical influences and humidity, the fit figure can be recalculated with acceleration factors standardized for industrial or military contexts. For example, high temperature and applied voltage cause the failure rate to increase. The most often cited source for recalculation the failure rate is the MIL HDBK217F, the Bible of failure rate calculations for electronic components. SQC Online. The online statistical calculators for acceptance sampling and quality control gives an online tool for short examination to calculate given failure rate values to application conditions. Some manufacturers of tantalum capacitors may have their own fit calculation tables. It should be noted that industrially produced tantalum capacitors nowadays are very reliable components. Continuous improvement in tantalum powder and capacitor technologies have resulted in a significant reduction in the amount of impurities present, which formerly have caused most of the field crystallization failures. Commercially available tantalum capacitors now have reached as standard products the high MIL standard C level, which is 0.01% 1000 H at 85 degrees Celsius and 0.1 failure per 107 hours at 85 degrees Celsius and recalculated in fit with the acceleration factors coming from MIL HDKB217F at 40 degrees Celsius and 0.5 is this failure rate for a 100 microfarads 25 volts tantalum chip capacitor used with a series resistance of 0.1 ohms. The failure rate is 0.02 fit. Lifetime. The lifetime, service life, load life or useful life of tantalum electrolytic capacitors depends entirely on the electrolyte used. Those using liquid electrolytes do not have a lifetime specification. Those using manganese dioxide electrolytes do not have a lifetime specification. Those using polymer electrolytes do have a lifetime specification. The polymer electrolyte have a small deterioration of conductivity by a thermal degradation mechanism of the conductive polymer. The electrical conductivity decreased as a function of time, in agreement with a granular metal-type structure, in which aging is due to the shrinking of the conductive polymer grains. The lifetime of polymer electrolytic capacitors is specified in similar terms to the non-solid electrolytic caps, but its lifetime calculation follows other rules which lead to much longer operational lifetimes. Failure modes and self-healing mechanism. Tantalum capacitors show different electrical long-term behaviors depending on the electrolyte used. Application rules for types with an inherent failure mode are specified to ensure high reliability and long life. Tantalum capacitors are reliable on the same very high level as other electronic components with very low failure rates. However, they have a single unique failure mode called field crystallization. Field crystallization is the major reason for degradation and catastrophic failures of solid tantalum capacitors. More than 90% of the today's rare failures in tantalum solid-state electrolytic capacitors are caused by shorts or increased leakage current due to this failure mode, the extremely thin oxide film of a tantalum electrolytic capacitor, the dielectric layer, must be formed in an amorphous structure. Changing the amorphous structure into a crystallized structure is reported to increase the conductivity by 1,000 times, combined with an enlargement of the oxide volume. The field crystallization followed by a dielectric breakdown is characterized by a sudden rise in leakage current within a few milliseconds, from nanoamp magnitude to amp magnitude in low-impedance circuits. Increasing current flow can accelerate in an avalanche effect and rapidly spread through the metal oxide. This can result in various degrees of destruction, from rather small, burned areas on the oxide to zigzag burned streaks covering large areas of the pellet to complete oxidation of the metal. If the current source is unlimited, a field crystallization may cause a capacitor short circuit. In this circumstance, the failure can be catastrophic if there is nothing to limit the available current, as the series resistance of the capacitor can become very low. Impurities, tiny mechanical damages, or imperfections in the dielectric can affect the structure, changing it from amorphous to crystalline structure and thus lowering the dielectric strength. The purity of the tantalum powder is one of the most important parameters for defining its risk of crystallization. Since the mid-1980s, manufactured tantalum powders have exhibited an increase in purity. Surge currents after soldering-induced stresses may start crystallization, leading to insulation breakdown. The only way to avoid catastrophic failures is to limit the current which can flow from the source in order to reduce the breakdown to a limited area. Current flowing through the crystallized area causes heating in the manganese dioxide cathode near the fault. At increased temperatures, a chemical reaction then reduces the surrounding conductive manganese dioxide to the insulating manganese oxide and insulates the crystallized oxide in the tantalum oxide layer, stopping local current flow. Failure avoidance. Solid tantalum capacitors with crystallization are most likely to fail at power on. It is believed that the voltage across the dielectric layer is the trigger mechanism for the breakdown and that the switch on current pushes the collapse to a catastrophic failure. To prevent such sudden failures, manufacturers recommend 50% application voltage rating against traded voltage, using a series resistance of 3 ohms V, or using of circuits with slow power-up modes.